Hello and welcome to the final lecture for Introduction to Astronomy. This is lecture number 20, and we are going to be talking, ironically, about the beginning, the Big Bang. So, we're going out with a bang. At the end, we're learning about the beginning. In today's lecture, we will learn about cosmology, what it means to study the evolution of the universe, and also about what Hubble time is. We'll learn about the rate of expansion of our universe and how that is related to gravity and dark energy. We'll then talk about how it all began with the Big Bang and how we have evidence for the Big Bang in the cosmic microwave background. So, cosmology is the study of the universe and how the cosmos themselves are changing and evolving. And this was seen after the discovery of Hubble's law that our universe was changing. It was often thought originally that our universe was just static and unchanging and that things were just in their place and that's what they would be. But now it seems that the universe itself has always been changing. So, with our tools brought to you by Einstein's theory of general relativity, our mathematical tools help explain that the universe can never be static when gravity is there, and it must either be expanding or contracting. That was what was shown in Einstein's original equation, shown below as this G sub uh, mu v. That was the law of an expanding universe, as was equal to all of the matter and energy in that universe. That the way that the universe was expanding or contracting was only equal to the matter and energy of that universe. But Einstein didn't quite like that. It gave him a philosophical quandary. It made him uneasy. And so he added a term called the cosmological constant, that term there in red, which would represent a hypothetical repulsive force that would balance gravity so that the universe could be in a state other than expanding or contracting. But he didn't like this eventually. He actually realized, maybe incorrectly later in his life, that it was a blunder. He called it his biggest blunder. And for some time, it seemed like the cosmological constant was indeed not something that was actually present. But after Hubble and Humason showed that the universe was expanding and accelerating, this need for a cosmological constant, something that acted as a repulsive force, actually began to take on significance. It may actually be needed to explain the universe as we see it using Einstein's theory of general relativity. So Einstein died before it was known that this cosmological constant may have actually had validity. So I'm going to introduce this concept of Hubble time. So we know from Hubble's law that there is this expansion rate. But imagine if we could turn back time and unwind that expansion. If something's expanding and you run it backwards, eventually it will go back down to a single point. Astronomers refer to this single point with all of the initial energy that ignited and expanded at the beginning of time as the Big Bang. So this age estimate for this period, which is the inverse of the Hubble constant, is what we call the Hubble time. And this references the estimated amount of time since that expansion began. But Hubble time is only the age of the universe if the rate of expansion is constant throughout time, and that assumes that the Hubble constant is indeed constant. But this turns out to not be true. The Hubble constant actually varies with time, so it's not truly a constant. In fact, the first cosmological philosophers believed that since the existence of gravity, since gravity exists, this would imply that the universe's expansion rate could not be constant, and that it should be decelerating or getting smaller with time because gravity is an attractive force. Now, this deceleration doesn't imply that we're not having an accelerating expansion rate, just that the rate of acceleration is itself getting smaller. Astronomers tried for decades to show that the universe was decelerating just as the cosmologists proposed. To do this, astronomers measured the distance and velocity independent of each other without using Hubble's law by observing Type 1a supernova. When they published their results in 1998, they shocked the world when they showed that Type 1a supernova in distant galaxies who had independently measured velocities and distances were fainter and therefore further away than Hubble's law predicted. They showed that Hubble's law didn't quite work, that the rate of expansion was not constant, that it changed with time. This discovery was groundbreaking, but what exactly does it mean for our understanding of the universe? So if the rate of expansion were getting smaller with time rather than getting larger, this would mean that those supernova, the Type 1a supernova that they measured, would actually appear brighter than Hubble's law predicted, since they would be slightly closer. But the observations showed the exact opposite, that they were actually getting dimmer than Hubble's law predicted. And so this meant that the expansion rate was getting larger with time, which implies that more space is being created at a faster rate now than during the Hubble time, and that objects are further away than Hubble's law predicted. From this data, we can reach a surprising conclusion that the universe is expanding and accelerating, and that this rate of expansion is accelerating too. The fact that the rate of expansion is accelerating was such a monumental discovery that it won the 2011 Nobel Prize in Physics. So now we have to talk about what could be causing the universe to be expanding, accelerating, and for that rate of expansion to be increasing. Acceleration requires energy, meaning that something is supplying the energy to the universe as it expands. Astronomers call this mysterious source of energy dark energy. But what is it? Well, it could be the cosmological constant. Hypothetically, there is energy associated with empty space in a vacuum. Particles flicker in and out of existence based on the rules of quantum mechanics. This has been shown and measured many, many times that empty space actually is not truly empty. But this hypothesis requires an immense number of vacuum energies to explain the rapid rate of expansion we see. There are a lot of other theories. Physicists are constantly proposing new theories for dark energy, but there's really no compelling evidence yet that can define what it is, just that it is present in the data, that something is causing this increasing rate of expansion. We're just not sure what it is. Whatever it is, its implication is that the Hubble constant is not constant, and that complicates our understanding of the universe. Also surprising, it appears that the acceleration of the universe itself did not begin precisely at the Big Bang, since there are other observed instances of a changing Hubble constant. So just like how stars are experiencing a tug of war between the force of gravity and their radiation pressure outwards, our universe has also been experiencing a tug of war between the forces of gravity and dark energy. Who will win? Well, from our observations, we find that in the earliest parts of Hubble time, in the earliest times of the universe, gravity overwhelmed dark energy and slowed the expansion rate, just as cosmologists predicted. But as galaxies formed and kept moving apart, the gravitational force between them began to weaken, and dark energy started to take over and increase the rate of acceleration as we see today. So, what will be the end state of the universe? Will the universe expand forever? Or will there be a point where it expands to and then turns back and begins to contract? All theories tell different stories, but they all hinge on how much matter there is, normal and dark matter, relative to how much dark energy there is in our universe. What is the energy budget of our universe really determines what the fate of our universe will be. So we can model these possible scenarios of what the universe will evolve into. So a closed universe would be a decelerating one that implies that the universe will stop expanding eventually and then begin to contract due to gravity. It will reach a maximum until it recombines again down into an infinitely small volume. This fate would be known as the Big Crunch. An open universe that is decelerating implies that gravity will never be strong enough to stop the expansion, and the expansion will continue forever through the final, although the final expansion rate will eventually be infinitely small. There's also an empty universe, which we call a coasting universe, which assumes that the Hubble parameter is globally constant, and neither gravity nor dark energy with the effect of will affect the overall expansion rate, and they'll operate in balance as Einstein biasly predicted. This would be our static universe, almost. And then our accelerating universe is the one that we appear to have, which has copious dark energy, where the rate of expansion increases with time and becomes faster and faster with no end. This scenario is precisely what the 1998 supernova results suggest, and this is where astronomers stand to this day. And so the end of that universe would be potentially the big rip, where everything just keeps being pulled further and further apart. Eventually, space will be expanding so rapidly that the very space between atoms will be ripped apart, and then atoms, the subatomic particles, potentially will be ripped apart, and the universe will just become a haze of energy that is almost infinitely far apart. That's not a very exciting one, but none of these are things that we will have to face. These are in the very, very far future. Trillions, quadrillions, quintillions of years in the future. So we don't quite know what will happen in the end of the universe, but we also need to try to understand what happened in the very beginning. So in the very beginning of our universe, there was only energy. This is where all of the matter came from. Cosmologists theorized that at the very beginning, from 10 to the negative 43rd to 10 to the negative 23rd seconds after the Big Bang, the universe was incredibly hot and dense, with temperatures ranging from 10 to the 31st to 10 to the 22nd Kelvin. So that's billions of kelvins. That is as hot as you can potentially get. And so as our universe only contained radiation and other forces, it began to expand and cool. Einstein's equations tell us that energy can create matter, and with a truly incredible amount of energy available within the first 10 to the negative 7 to the first 100 seconds of the universe, all of the protons and antiprotons and electrons and positrons in our universe were created in equal amounts. This then started a war between matter and antimatter, which matter won because we have a universe of matter today. There is much more matter than there is antimatter. But astronomers can't astronomers and cosmologists can't quite explain why there is more matter than antimatter when in theory there should have been exactly equal amounts created from the initial energy. This is what astronomers call the baryon asymmetry problem, and it has not been solved today. It still exists. Why do we have a universe that contains matter instead of an equal amount of matter and antimatter? A little bit after the Big Bang, as the universe expanded and cooled, it then reached the conditions necessary for nuclear fusion to occur. And so we began to have some complex nuclei appear in the primordial soup before stars had even formed. We had deuterium, which is heavy hydrogen. We had some lithium, and we even had some helium nuclei form within the first 3 to 4 minutes of the Big Bang. The amount of helium nuclei which formed, about 25% of the total mass of the universe, is crucial evidence for this theory, since there is far too much helium in our universe to have come from star formation alone, and the Big Bang theory accurately predicts the observed amount of helium that is 10 times more than there is from just stellar evolution. So the Big Bang can explain why we have so much helium in our universe. So, what is our observational evidence for the Big Bang Theory? We can't have a scientific theory without rigorously following the scientific method, and so we need some observational evidence. And so, though the first observations which helped confirm this theory come from the amount of helium in our universe, it is what occurred nearly 380,000 years after the Big Bang, which provides the most indisputable evidence for this theory. So, while before the universe, right after the Big Bang, the temperatures of were right for the fusion of helium and lithium. And so when everything was still dense enough for that fusion to occur, the universe itself resembled the interior of a star. It was hot and it was opaque plasma, which trapped radiation. Whenever a photon tried to be emitted, it would be immediately absorbed because the density of matter was so high. But after a few 100,000 years of expansion, the temperatures had cooled down to about 3,000 Kelvin, and the densities in the universe had decreased to about 1,000 particles per cubic centimeter, which allowed for electrons to merge with nuclei and form the first stable atoms. This meant that the universe opened up in a sense between matter and radiation could now move freely through the universe without interacting with matter super quickly. If our model of the Big Bang is true, theorists predict that we should find an afterglow of this very early universe radiation, which is being emitted at the very moments photons were no longer trapped by the matter, which we call the decoupling time. When did photons finally have the densities around them necessary that they could move without being absorbed? So when the photons were finally free from matter and could spread throughout the universe, it created this afterglow. And it turns out that this afterglow was detected by accident. In the 1940s, Ralph Alpner and Robert Herman calculated that after 14 billion years of expansion, this afterglow would now be at radio wavelengths and could be detected everywhere in space isotopically. And but there was no method available at the time to detect this radiocosmic background. And this idea was forgotten until the 1960s when Arno Penzias and Robert Wilson at Bell Laboratories were using microwave antenna to study supernova. They were shocked to find that no matter where they pointed in the sky, they found a nearly uniform background noise in every direction of the sky. And generally, radiation has a source. So after tirelessly showing that this microwave background was not from something in their telescopes, the predictions of Alpher and Herman were recalculated, and it was determined that the radiation from photon decoupling was a spectrum, and that spectrum peaked in the microwave. And these observations, which are referred to as the cosmic microwave background, were a part of this early radiation from the Big Bang. This observation directly confirmed that the universe began as a hot, uniform state, and it provides direct support for the age and evolving nature of the universe based on the current observations of the spectrum and intensity of this cosmic microwave background. It is pretty much the most perfect black body radiation source that you can have, if you remember that from the beginning of our course. We have now reached the end of our lectures. We have talked about the history of astronomy from the very first ideas looking up at the sky to the creation of the scientific method and the refinement of those ideas into theories. And then we created the technology necessary to further refine those theories. And we now know that the Earth orbits the sun, which is an average star in the universe, or which is an average star in our Milky Way spiral galaxy, which is itself one of billions of galaxies in the universe, which is undergoing great change and expansion, and that the universe itself and all matter and all galaxies and all stars were once compressed into a single point. And all of this comes from looking up at the sky and wondering and thinking and studying and the scientific method and just human ingenuity and curiosity. And I really hope that this course has really opened your mind and your eyes to the beauty of astronomy and the power that this scientific field has to explain the universe around us and how we got here. Why we are here is up to us to decide, but how we got here, that's from astronomy. So thank you so much for taking this course and engaging with the material. I hope you have had a wonderful time. I have had a wonderful time teaching you all. Thank you so much, and have a wonderful rest of your life, I guess. And enjoy the night sky. The end.